In this video, I wanted to do an overview of zener diodes. That's zener. Zener diodes are much like the diodes we've been working with up till now, simple p-n junctions that have been modified slightly to function a bit different. Schematically, they look almost the same, with one little change. These two lines get drawn on there. Other than that, they look pretty much the same, and it is still anode and cathode. One of the big differences with zener diodes is they function in reverse bias. I thought I'd write that so that you understand what I was talking about. There, reverse bias, meaning that up till now, all the diodes we've worked with functioned or were calculated into our circuits when they were forward bias. This one's reverse bias, and in essence, if I had to draw an equivalent for it, it would be this, believe it or not. And I think this explains it better than anything else. A DC power supply, and if this was a 5-volt DC power supply, that means in the reverse direction, this zener diode has a 5-volt fixed drop. It's within a range. If I were to sort of try to graph it or show you the characteristics curve for it here, and I'll pick another color so you can get a comparison. There we are. It does something like this. Remember, this is in reverse bias. It doesn't destroy itself. This is where it wants to function, and somewhere about here would be the 5 volts. And what you'll notice looking at this picture is that this 5-volt mark is where, for a very small change in voltage, we are getting a very big change in current. So you'll see here, if we only have a small voltage change, you can see there's a huge change in current. So this is sort of like the diodes the other way, but this means it's got, instead of a 0.7, it's got a fixed 5-volt drop, which makes it very handy for working with as a regulator. Sorry, I was changing my pen color. So some interesting things, or some points to pay attention to here. There's a point right here, and you'll see there's a current. This here would be current, and this here will be voltage, and there'll be a current here. For example, let's say 5 milliamps. And then down here, there's one, and this might be 70 milliamps. In this example, 5 milliamps is called the knee voltage, or K, and wow, that's actually a 7, eh? Alright, hold on. There. 70 would be the max current. And then in here, there'd be a rated current. Normally not given any notation, it's just given as a current and a voltage. So when you get specs for a diode, in this case, they might say that that the voltage of this zener is equal to 5 volts at, believe it or not, that's an at symbol, at 5 milliamps. And of course, looking at the graph, then you could say voltage of this zener at max might be 5.8 volts at 70 milliamps. So you can see that there's sort of a relationship here between voltage and current, which gives us the ability to calculate impedance, or some sort of a Z value, right? Z being change in voltage over change in current, right? So what we're going to do is do a bit of math with these. look at impedance values and put these into circuits and see how they work. But generally, this is a quick and badly drawn overview of how zeners work.